Hello everyone, welcome to this lecture in Differential Calculus. Today we are going to talk about partial derivatives of function of two variables and the concept of differentiability. So first let us talk about the partial derivative of function of two variables and then one can extend it to any number of variables. The concept is very similar to function of one variable. Okay, so when we have say a function of two variables, then we calculate the partial derivative with respect to one of the variables, independent variables, by treating the other independent variable as a constant. Okay, or we fix that second variable. So the partial derivative of a function of two variables x and y with respect to x at a fixed point x naught y naught is given by this partial derivative of f with respect to x at x naught y naught equals to limit h tends to 0 f of x naught plus h y naught minus f of x naught y naught by h, provided the limit exists. So you can see that this on the right hand side we have fixed y naught y as y naught as a uh, fixed constant, because we are trying to find the partial derivative with respect to x. So y is equal to y naught is fixed, and the rest of the definition then is very similar to a single variable, where this is limit h tends to 0 on the change in the function values to change in the domain value. Okay, so it's like the slope of the secant when h goes to 0, so it will give us the slope of the tangent line in the direction of x when y is equal to y naught is fixed. Okay, so geometrically, if you say that if there is a surface, say this given in gray, and then if I fix y is equal to y naught, that means if I cut this surface with a plane y is equal to y naught, then the surface will be cut and it will give a curve. Okay, and this uh, curve is z is equal to fx y naught, because y is equal to y naught cut this surface. Okay, and this blue curve, which is the intersection of y is equal to y naught plane and this surface z is equal to fxy, this curve lies in the xz plane. The horizontal axis is the x-axis and the vertical axis will be the z-axis, and so we can treat it as a function of one variable, and then at this point, which is x naught y naught, we can calculate the slope by calculating the derivative with respect to x. So what we get is the slope of this tangent line at x naught y naught, which is given by this formula. Okay, so basically partial derivative of a function with respect to x at x naught y naught gives us the rate of change of the function with respect to x when y is held fixed at y naught. Okay, so if you have two variables and you are partially differentiating with respect to one variable, then you keep the other variable fixed. Okay, and then you can differentiate with respect to the one variable just like the ordinary derivative. Okay, so remember that the vertical plane y is equal to y naught will cut this surface in the curve. Okay, f of x y naught, just this blue curve as shown here. Okay, and this partial derivative written as partial f by partial x at x naught y naught, and there are some other symbols or notations which we use, that we also write this as partial f by partial x at x naught y naught, or f subscript x. So f subscript x is also means the partial derivative of function with x at x naught y naught, or because z is equal to fxy, so we can also write z derivative x. Okay, or partial z by partial x x naught y naught. So all these notation just represent the same thing, that it is the partial derivative of function with respect to x variable. Okay, Similarly, we can define the partial derivative of function with respect to y at the point x naught y naught, and so we are differentiating partially with y. So we keep the x is equal to x naught as a fixed. Okay, so partial derivative of function with y is the uh, limit h tends to 0 of the slope of the secant, where now the change is in the y. Okay, provided that this limit exists. Okay, so again geometrically you have a surface, and we cut this surface with x is equal to x naught plane. Okay, so when x is equal to x naught plane, we'll cut the surface and this blue curve will be generated. Okay, and then at the point x naught y naught, if we draw a tangent line in the direction of y, okay, then the slope of this tangent is given by this. Okay, so what we are now in this case getting is the partial derivative of function with respect to y at x naught y naught gives the rate of change of the function f with respect to y when x is held fixed at x is equal to x naught. Okay, so it is the slope of the tangent line at the point x naught y naught in the direction of y. Okay, and again note that the vertical plane x is equal to x naught cuts this surface z in the curve f x naught y. Okay, so this blue curve is f of x naught y. Okay, and the partial derivative gives the rate of change of function with respect to y when x is held fixed at x naught. Okay, so these are the two partial derivatives. Okay, so similarly we can extend it. Say you have a function of three variables, f is a function of x y z, then we can have partial derivative with respect to x or y or z. And say if you calculate the partial derivative with respect to x, then you keep y and z as fixed. Okay, and you then differentiate with respect to x. So this definition is based on keeping the other variables fixed and then finding the derivative with respect to one variable. So it's very similar to functions of one variable. So all the rules that we applied during calculus for one variable, all those rules are applicable or are true here as well. Okay, so we can algebraically calculate the derivative with respect to one of the variables by treating other variables as a constant. Okay, so what we have found here is uh, two tangent lines at the point on the surface. Okay, so one tangent line gives us the uh, and the slope of the tangent that we calculated is in the direction of x, and the other is the slope of the tangent in the direction of y. Okay, so if you have a surface and we calculated say partial derivatives at this point x naught y naught, then what we calculated is slope of this tangent which is in the direction of positive x, and the slope of this tangent line which is in the direction of positive y. So one question arises that the only these two tangents are possible at this point. Okay, so the answer is that there can be other tangents lines as well, okay, which are not in the direction of x or in the direction of y. Okay, so like we can cut this surface with the plane y is equal to x, and then we will have a curve in this direction, and then we can calculate a tangent line in this direction as well. So there can be infinitely many tangent lines at this point, because this point can be approached by infinitely many directions. Okay, uh, now the second question that arises is that do all those tangents or tangent lines they lie on the same plane, or I can say that uh, do these two tangent lines generate uh, uh, the two tangent lines, these two tangent lines, if they generate a plane or they lie on a plane, does that plane is a tangent plane to the surface? Okay, so this is my question, that is the plane and these tangent line determine is that plane is a tangent plane to the surface at this point x naught y naught. If it is so, that means all the tangents will lie on that plane, and so this function will be differentiable at this point. Okay, so soon we will talk about this concept of differentiability and learn that how to find the tangent plane if it exists. Okay, so if they determine a tangent plane at this point, okay, then we say that function is differentiable at this point. And so before we talk about this, let us take one example to find partial derivatives first. That find the value of partial derivative of function with x and partial derivative of function with y at the point 4 minus 5 if function is given this. Okay, function of x and y. So as I said that partial derivatives work in the same way we do the ordinary derivatives, but if say we have to differentiate with respect to x, then we treat y as a constant, or if we have to treat or that take derivative of function with respect to y, then we treat x as a constant. Okay, remember that x and y are two independent variables and they are not functions of each other. Okay, the partial derivative of function with respect to x. So if we are differentiating with respect to x, then we will treat y as a constant, and then we just apply the rules of ordinary derivative. Okay, so derivative of x square with x will be 2 times x. Derivative of 3xy, and y is treated as a constant when we differentiate with x. So it is simply derivative of x with x 1, and 3 times y is a constant, so 3 times y, and y minus 1 will be treated as a constant, so its derivative with x will be 0. Okay, so the partial derivative of function with x is 2 times x plus 3y, and then if we have to calculate at this point, so x is 4, y is minus 5, so we'll get the value of partial derivative of f with x at 4 minus 5 by putting this value here. Okay, so partial derivative is minus of 7. Okay, so slope of the tangent line at this point in the direction of x-axis is -7. Okay, and so similarly, if we have to differentiate this partially with respect to y, this function, then we will treat x as a constant. Okay, so this x square derivative will be 0, 3xy, 3x will be constant, y derivative will be 1, so 3x, and y derivative with y will be 1, so plus 1, and this constant derivative is 0. So 3x plus 1, and at this point then x is 4, so we'll get slope as 13. Okay, so this is by simple process, but same we can do with the definition also. So let us test this through the definition of partial derivatives. Okay, so by definition, partial derivative of function with respect to x at any point x naught y naught is this limit, provided this limit exists. Okay, so at this point 4 minus 5, so we can substitute x naught as 4 and y naught as minus 5. Okay, and since function is given, so we can calculate a function at 4 plus h minus 5 and function at 4 minus 5. So with x value 4 plus h, y value minus 5, we can calculate this. Okay, so function at 4 plus h minus 5, so put x as 4 plus h, y as minus 5 in this. Okay, so what we get is this h square minus 7h minus 50, and function value at 4 minus 5, so put x as 4, y as minus 5. Okay, or simply put h as 0 here, so we'll get, okay, so we'll get minus 50. Okay, so f at 4 minus 5 is minus 50, so we can substitute these two quantities on the right hand side here and find the limit. Okay, so if you substitute, cancel out this 50, and then we can cancel out h as h is non-zero, and so taking h tends to 0, this will give minus 7. So it is the same value we obtained algebraically. Okay, so by definition also it gives the same result. Okay, and similarly we can also calculate partial derivative with respect to y by the definition of partial derivative. Okay, so this part I am leaving. You can start from here. Partial derivative function with y will be limit h tends to 0, f of x naught comma y naught plus h. Okay, so the change will be in y naught minus fx y naught over h. Okay, so we can also find, and you will find that it will give the same value as we calculated in the previous slide. Then say one more example, that the plane x is equal to 1 intersects the paraboloid this in a parabola. Okay, find the slope of the tangent to the parabola at this point. Okay, so given this paraboloid x is equal to 1 is a plane, and so x is equal to 1 will cut this surface into a curve, and that curve is a parabola. And then uh, on this parabola at this point 1 2 5. Okay, so that means it will satisfy x is equal to 1. Okay, x is 1, and it will also satisfy this because it is lying on this surface. So x1 y2 z5. Okay, satisfied. So this point is on the curve as well as surface. Okay, and we have to calculate the slope of the tangent to the parabola, means this curve. So when x is fixed, that means we have to find the derivative with respect to y at this point. Okay, so geometrically you have a paraboloid, and the plane x is equal to 1 will cut this paraboloid into this blue curve, which is a parabola, and on this curve there is a point 1 2 5. At this we have, if we draw a tangent line, then what is the slope of this tangent? Okay, so when x is equal to 1 is fixed. Okay, so one of the variable is fixed, then that means we are trying to find the slope in the other direction, in the direction of y. So we have to differentiate this partially with respect to y, and then calculate the slope at this point. Okay, so the slope is the value of partial derivative z with y at 1 2. Okay, so you can simply differentiate this with y, which is treating x constant, so it will give 2 times y only, and at the point 1 to 5, or simply 1 2 because the y only, so it will give 4. Okay, so this way, or you can also do that because they intersect in a parabola, so you can calculate the equation of parabola, which will be z is equal to 1 plus y square, and so then you can differentiate with y, again it will give same thing. Okay, now one important concept here in partial derivative uh, is that uh, we know that in function of one variable, uh, differentiability implies continuity. Okay, and this is also true in higher dimensions. Okay, in higher dimensions also, if you have a function which is differentiable, it must be continuous. Okay, but differentiability in high dimensions need a stronger definition in the sense that even when function is not continuous, partial derivatives may exist. Okay, so here's important result, that a function f of x y can have partial derivatives with respect to both x and y at a point without the function being continuous there. Okay, uh, just because partial derivatives are slopes only in uh, the direction of x-axis and in the direction of y-axis. Okay, but continuity means we have to approach the point from all directions. Okay, so even when the function is not continuous, okay, even then we can have slopes in the direction of x-axis and slopes in the direction of y-axis. So both partial derivatives with respect to x and y can exist even when function is not continuous at the point. Okay, say for example, to show this, let you have a function this which is 0 when xy product is non-zero, and 1 when xy product is 0. Okay, so along the x-axis and y-axis the function value is 1, and for every other point which is on not on the axis, the function value is 0. Okay, so find the limit of function xy as approaching 0 0 along the line y is equal to x. So that's one question. Second is prove that the function is not continuous at origin. Okay, and third, show that both partial derivatives f derivative x and partial f derivative y exist at origin. Okay, so function is not continuous at origin, but still the partial derivative exists. Okay, so let us first see what exactly is this function. Okay, through this graph. Okay, so function takes value 1 when product xy is 0. So product xy will be 0 when either y is 0, that means points are on the x-axis, or when x is 0 means points are on the y-axis. So along the points which are on the axis, the function value is here. Okay, 1 at a height 1, z is equal to 1. Okay, and for all other points in the domain, okay, where the product xy will be non-zero, okay, say 1 1 point, 2 1 point, and so on, the function value will lie in the z is equal to 0 plane. Okay, so in here all these points are points where product xy will be non-zero. Okay, so along the axis the function values are up here. Okay, and otherwise they are on the ground. Okay, so first question is that find the limit of function as xy approaches origin along this line y is equal to x. So this is the positive y-axis, x-axis. So x is equal to y is line here. Okay, so when we move along x is equal to y from here towards the origin, okay, the points will be like 4 4 3 3 2 2 1 1 and so on. Okay, so xy product is non-zero, so we will get that the function limit is 0. Okay, so you can see that we are moving in the ground and we will reach here. Okay, so this limit value must be 0. Similarly, prove that the function is not continuous at origin. Okay, uh, along this line the value is 0. Okay, but the function value at 0 0 is 1. Okay, so continuity is not there, and both partial derivative exist. Okay, so let's just see this by definition. Okay, so first is that uh, the function is constantly 0 along the line y is equal to x except at origin. So we have that this limit must be 0. Okay, so as I said, as we move along y is equal to x line, y is equal to x line will be here. Okay, so as we move along y is equal to x line toward origin, okay, then the function values are 0 0 0 so on 0. So we'll reach here. Okay, so this limit value must be 0. Second point is the continuity. Okay, the function value at 0 0 is 1. Okay, that origin the function value is here. Okay, but along this line we calculated that the limit is 0. Okay, but for continuity the limit, if it exists, it must be equal to the function value. Okay, but this is not equal, so function cannot be continuous. Okay, the third is the partial derivative, and by definition partial derivative of function with respect to x at origin means we have to solve this limit h tends to 0 f of h0 minus f of 0 0 by h. Okay, and when x is h, y is 0, the product of these two is 0. Okay, so this will be satisfied, so z will take value 1, so f of h0 must be 1. Okay, and f of 0 0, so again this will be satisfied, and so f of 0 0 is also 1, and h is non-zero, so this numerator is 0, so limit value will be 0. Okay, similarly, if we calculate partial derivative with y, so it is f of 0h minus f0 0 over h, and limit h goes to 0. So f of 0 comma h, again 0 and h, so product will be 0 and we get z as 1. Okay, so this value must be 1. F of 0 0 is 1, so this limit is again 0. So you can see that both partial derivatives are 0, and so they exist even when the function is not continuous. Okay, so you can also see from here that the partial derivative with respect to x at origin simply means the slope of the curve in the positive direction of x-axis, and slope here is 0. Okay, and similarly partial derivative with y at 0 0, so at origin the slope in of the curve in the direction of y, which is again 0. Okay, slope here is 0, it's a horizontal uh, curve or straight line. Okay, so both slopes are 0 and these slopes exist. Okay, and even when the function is not continuous. So this is a important concept because in higher variables continuity means that the limit, if it exists, it should be uh, same from all directions. Okay, but partial derivatives, we are only calculating in some particular direction. So partial derivatives can exist even when function limit is not there or function is not continuous. Okay, so before we talk about differentiability, just two definitions here. One is the mixed derivative theorem, and it says that if function and its partial derivatives f derivative x, f derivative y, or the second order derivatives f of x y and f of yx are defined throughout an open region containing point a b and are continuous at a b. Okay, so if the function and its partial derivatives of first and second order they exist and are continuous at the point, then the order in which partial derivatives are calculated is immaterial. Okay, so they give the same value. Okay, so functions partial derivative with x and then with y at ab, or functions partial derivative with y and then with x at ab, they give the same result. Okay, so this continuity is important. Okay, so if functions are not continuous or the partial derivatives are not continuous, then they may end up with different result. Okay, so this is one result. Okay, and higher order derivative we can calculate very similar to how we calculate the first order derivatives. Okay, so we can differentiate function with x keeping other variables constant, and then the result can be differentiated with respect to x or with respect to y to calculate higher derivatives. Okay, so not just second, we can continue this concept to calculate third order, fourth order derivatives and so on. Okay, the second important definition here is the tangent planes. Suppose function is has continuous partial derivative, an equation of the tangent plane to the surface at the point x naught y naught z naught is given by this equation. Okay, z minus z naught is partial derivative of f with respect to x at x naught y naught times x minus x naught plus partial derivative function with y at x naught y naught multiplied with y minus y naught. So this is the equation of uh, tangent plane to the surface at point x naught y naught z naught. Okay, and so when we talk about differentiability, uh, then we say that if this plane, the tangent plane, if this approximates the function value on the surface for all xy points near to x naught y naught, okay, then we say that function is differentiable at x naught y naught. Okay, so if the uh, function values on the surface can be approximated by the tangent plane for points near to the point where tangent plane is drawn, then function is differentiable. Okay, so remember here z is f of xy and z naught will be the function value at x naught y naught, so z naught is f of x naught y naught. Okay, so once we know this definition of tangent plane, then now we are ready to uh, define what exactly differentiability is and how we can check whether a function is differentiable at a point or not. Okay, so a function f of x y is differentiable at a point x naught y naught if the partial derivatives exist. Okay, so both the partial derivative with x and partial derivative with y at x naught y naught exist, and this holds in which epsilon 1 epsilon 2 tends to 0 as xy tends to x naught y naught. Okay, so when x goes to x naught and y goes to y naught, this epsilon 1 and epsilon 2 they also go to 0. Okay, so what this statement says is that uh, these first three terms are actually the linearization of the function. Okay, and this xy are any points near to x naught y naught where this tangent plane is drawn. Okay, so this is, you remember, z is equal to z naught plus fx x minus x naught plus fy y minus y naught. So this is the equation of tangent plane, and here xy are the neighborhood points to x naught y naught. So this is a uh, function value on the surface. Okay, so that means whenever the function value on the surface can be equated with the uh, value on the tangent plane with some marginal error, okay, where error goes to zero when the neighborhood point approach the point where tangent plane is drawn. Okay, so if we can approximate the function value in the neighborhood of x naught y naught by the tangent plane, then we say that function is differentiable. Okay, so and we call function differentiable if it is differentiable at every point in its domain, and if it is differentiable at every point in the domain, then we say that the graph is a smooth surface. Okay, so this concept is true that a function is differentiable, then function is continuous at x naught y naught. Okay, so differentiability implies continuity. Okay, the converse may not be true. Okay, so for differentiability, there are three conditions. One is that the partial derivatives must exist, and the third is that the value of the function at the surface can be approximated by the value on the plane for points which are very close to the x naught y naught. Okay, if this is true, then we say that function is differentiable at x naught y naught. Otherwise the differentiability will fail. Okay, so if you have to prove that function is differentiable, then you just need to prove these three conditions are true. Okay, and if you have to prove that function is not differentiable at a point, then uh, uh, if either these three conditions fail, then we will have that result. Okay, so I'll just take one example to show that even when the partial derivatives exist, okay, the third condition fails, and so the function is not differentiable at a point. Okay, so show that the function f, where function is given by this, is continuous, possess both partial derivatives at origin. Okay, so continuity at origin, uh, but is not differentiable at origin. Okay, so this function is continuous at origin, has both partial derivative at origin, but the function is not differentiable at origin. Okay, so first let us prove the continuity of this function at origin. uh, for continuity, by definition, we say that for every epsilon positive there is a delta positive such that the modulus of fxy minus f of 0 0, f of 0 0 is 0. So just modulus of this is less than epsilon whenever 0 less than root of x minus x naught square plus y minus y naught square is less than delta, and x naught y naught is 0 0. Okay, so simply x square plus y square. So to prove that both these conditions hold for every epsilon, there exists a delta as a function of epsilon. We can prove this by taking polar coordinates. Okay, so if I use x as r cos theta and y as r sin theta and solve this left hand side modulus, okay, so xy by root of x square plus y square by this substitution. Okay, so x as r cos theta, y as r sin theta, and x square plus y square will be r square, so root will be simply r. So one r will cancel out and we'll have r cosine theta sin theta, and so I can divide with 2 and multiply to write it sine of 2 theta. Okay, and because sine of 2 theta is always less than equal to 1 in modulus, so this will be less than equal to r by 2, and because r is x square plus y square is r square, so r is root of x square plus y square, which is equal to delta from here. So if I choose delta by 2 to be epsilon, okay, so that means if I choose delta to be 2 times epsilon, so both these conditions are automatically satisfied because this modulus will be less than epsilon and this root will be less than delta. Okay, so by choosing delta to be epsilon by 2, these both conditions are satisfied. Okay, so for every epsilon, delta is 2 times epsilon can be chosen so that this holds. That means that continuity is there at origin. Okay, so clearly function is continuous at origin. Now the second is that the partial derivatives exist at origin. So by definition, the partial derivative of function with x at origin, okay, is given by this definition: limit h tends to 0, f of h0 minus f of 0 0 by h. Okay, and with this the function, so when f of h0, so x is h, y is 0, so this will be satisfied. Okay, h square plus 0 is not equal to 0. Okay, so because h is non-zero, so this will be satisfied. So we'll have function value this with xh y0, so numerator will be 0 and denominator will be non-zero, so it will give 0. Okay, so for f of h0 is 0 from here. Okay, minus f of 0 0. Okay, so at 0 0 function is 0, so simply 0. Okay, and so numerator is 0, so we get limit value as 0. Similarly, partial derivative function with y at 0 0 is limit h tends to 0, f of 0h minus f of 0 0 by h. F of 0h again, when x is 0 yh, this will be satisfied for h non-zero, and so x0 yh, so again numerator will be 0, so f0h is 0 from here, and f of 0 0 is 0 from this second result. Okay, so this will be 0. Okay, so both partial derivative exist at origin and their value is 0. Okay, uh, now third is the differentiability at origin, and for differentiability, since both partial derivatives exist at origin, so the function will be differentiable if the third condition is also satisfied, and the third condition says that the function value on the surface can be approximated by the function values on the plane. Okay, uh, uh, with the condition that as xy approaches this, epsilon 1 epsilon 2 also tends to 0, and this has to be held at origin. Okay, we are talking about differentiability at origin, so x naught is 0 and y naught is 0. So first let us put x naught 0, y naught 0 everywhere, so this will be f of x 0 0 into x. Okay, similarly it will be f of y 0 0 into y. Okay, and then we can substitute these values, we have already calculated them. Okay, so using x naught y naught as 0 0, so left hand side is f of xy for xy points near to origin, and equal to f of 0 0 plus fx 0 0 into x plus fy 0 0 into y. So that's the equation of the plane plus this. Okay, epsilon 1 x plus epsilon 2 y, where both epsilon 1 and epsilon 2 tends to 0 as xy tends to 0 0. Now these values are known. F of 0 0 from the function is 0, fx partial derivative with x at origin and partial derivative with y at origin we have already calculated, they are 0. Okay, so all these three numbers are 0, that means the tangent plane is z is equal to 0 plane. Okay, so and the function for xy which are close to 0 0, so that means when x and y, this point is non-zero point, so function is given by this xy by root of x square plus y square equals these three quantities are 0, so these terms will only end up with epsilon 1 x plus epsilon 2 y, and where epsilon 1 epsilon 2 tends to 0 when xy tends to 0 0. Okay, so function will be differentiable if this holds true for uh, every path in which xy goes to 0 0. Okay, so if you can find some path by which this, when xy approaching origin, this do not hold true, this do not satisfy, okay, and then we say that function is not differentiable. So in this particular case, if I choose the path y is equal to m times x and then take limit x goes to 0, so if I put y as mx here and here and also on the right hand side, and on the right hand side then I can take x common and I can divide with x because x is a non-zero number, and then I can cancel out x throughout. Okay, so that will give me limit x tends to 0, and on cancelling out x from here it will be y is mx, so I will get 1 m here in the numerator, and here I will get m squared, so 1 plus m square root. And on the right hand side limit x tends to 0 epsilon 1 plus epsilon 2 m, because y is mx and then x is common, which I took to other side and cancelled out. Okay, so when x goes to 0, then epsilon 1 and epsilon 2 also goes to 0, so this right hand side will go to 0. But when limit x goes to 0, the left hand side uh, remains m over root of 1 plus m square. Okay, just because when xy goes to 0 0, these two go to 0 as well. Okay, now this do not hold for arbitrary m. Okay, so uh, this only holds for m is equal to 0, and for like m is equal to 1, m is equal to 2, so on, this equality do not hold. So uh, this result do not hold for arbitrary values of m. Okay, so there are paths for which this do not hold. That means the function values on the surface cannot be approximated by the values on the plane. Okay, so we say that the function is not differentiable at the origin. Okay, graphically if you see, look at this function, it is this drawn in cyan color, and this plane was z is equal to 0, so this is z is equal to 0 plane. Okay, uh, both the partial derivatives exist at origin. You can see that the slope in the x direction is 0 and slope in the y direction is also 0 for this function. Okay, so both partial derivatives we calculated to be 0 0, and uh, you can see that along, say, y is equal to x line, okay, which is along this x-axis, y-axis, the function values in the neighborhood cannot be approximated by the plane. The slope changing very rapidly at close to origin. Okay, so function is not differentiable at origin in this case. So this was the concept of partial derivative and differentiability. In the next lecture, we will talk about the concept of maxima and minima for functions of two variables. Till then, have a very good day.